Alright, so the physicist Michael guy in comments did say he was going to be making some comparing my model to their model thing or something video. And so we'll see what this is, okay. And I'll just do this now. Maybe I'll do more later. I'll try to just sew the videos together, but I just thought it would be interesting to do a cold watch and see what we get.
Hi everyone. In this video, we're going to do a side-by-side comparison of...
Alright, and so the only difference between the two models regarding momentum, in my opinion, is the idea of negative momentum. I don't think there's anything that allows for undue momentum. The gun's recoil doesn't undo the bullet. It just doesn't happen. They're real motions in the universe. They have to be accounted for by real energy that produces them. So there's no unenergy. There's just energy. You can turn right and then you can turn left. Both of them required energy to produce. The fact that you ended up with no outcome in terms of your direction doesn't mean the universe wasn't impacted. Of course it was. You did move in the universe. You moved that way. You pushed stuff that way. Then you went this way and you pushed stuff that way. Those are real events. Okay. Let's see, this volume might be a little bit higher than necessary. This little thing gets in my way. Annoying. Alright, so that's probably sufficient. And so, continuing, sorry.
Two models of momentum. One being the standard physics textbook definition of momentum, the model first described by Isaac Newton.
So that's what I'm going to say is just a lie, okay? Your description of momentum is not Newton's. Newton did not believe in anti-momentum. He believed that right turns are real and then left turns are real, and that you can have a circumstance where, yes, if you turn left and then you turn right, you'll be going straight. But he didn't believe that you have created any circumstance where you can say you have zero momentum because you have something going this way and something going that way. That he didn't believe.
And the other will be an alternative view of momentum that has been presented by a small but vocal group of individuals in the comment section of some of my videos.
So strange that he can't, he's already made it public that he's going to do this lever experiment, and it's like he just can't say the words DraftScience. I mean, frankly, this isn't promoted by a group of individuals, okay? There's not some collective people who all joined together, because they believed in something. It's me, okay? And now a few people who I've convinced, and that's it. But let's not pretend this is coming from any group. Okay, it's really not.
If you're not familiar with some of these claims, that's okay. I will try to present their model of momentum as accurately as I can.
Okay, so I have made 10 5-minute videos explaining all of the reasons, and there's numerous reasons why kinetic energy fails the reasonable test, and he could just link to one of those explanations for why I don't think it works. The very fact that they don't understand how gravity works, frankly. It's a time-dependent force. But whatever.
Not presenting a straw man argument. Hopefully all these statements that I will make about their model they would agree with.
So, yeah, no, we're not going to agree that Newton had anything to do with mv squared nonsense, because he didn't.
And then we can use this as a test case for comparing two models of a physical phenomenon and find ways to experimentally test the points.
So this argument, again, as I've already pointed out in numerous videos, I've drawn the pictures in numerous videos that, yes, if I do something inside of a spaceship, I can make a certain thing happen. But that doesn't mean that now if I release the energy outside of the spaceship, that something different will happen to the bigger universe. So the two things of taking something in isolation and then taking something as an absolute statement is like the difference between Galilean relativity and Einsteinian relativity. The difference is profound. Okay, it's not a minor difference, it's a gigantic difference. Accepting the fact that there's relative relationships between objects, that I'm relatively moving in the same direction as this pen all the time, that it has the same energy, it's being affected by the same force laws that I'm being affected by, and then I can just change the local ones. Okay, all I want. I can change the local ones all I want, but we still have an absolute motion in the universe. That's Galilean. There's still an absolute universe. I mean, Einsteinian is there's no absolute universe. There's no such thing as something standing still.
Where these two models differ, so we can identify which one is able to make accurate predictions of how different physical systems will work. So
if the prediction is free energy, it's a disqualified theory, and that's the prediction. I'm just saying you cannot conserve both of these entities when you, every single time you transfer energy from objects with different masses, you have to kill momentum or you have to kill kinetic energy as a theory. Both of them cannot survive. Both of them will not conserve. So it's clearly a contest between momentum and kinetic energy.
We're going to start by reviewing the standard textbook definition of momentum, and let's go right back to the source, Isaac Newton's key work, the Principia.
Okay, so let's understand his key work. He says you want to go twice as fast, you apply twice the force. You want to go 3 times as fast, you apply 3 times the force. Clearly defining that force equals your velocity in this case, because we're not changing your mass. But if we were going to change your mass, it would be force equals momentum. The change in your momentum is the force, the end. Okay, that's the definition. And he's just going to play a game with semantics and words here.
I'm going to do a bit of a deeper dive into this because the proponents of this alternative model that we'll be discussing later on claims that theirs is the model that Newton used, and this is simply not the case as well.
Well, whatever. We'll see. Again, let's understand there's no way Newton had any concept of mv squared, okay, or v squared at the time. There's no way. He opposed it, okay? It was obnoxious to his physics. It was basically a challenge to his physics. So there's just no way to convert this into Newtonian mechanics. It is not Newtonian mechanics.
We'll see. There are fundamental disagreements with how this alternative model uses momentum. I'm going to leave a link to the English translation of Newton's Principia in the description, along with page numbers for some of these excerpts, so you can...
And let's understand, in frank truth, go read it, okay, and you'll see what a lot of people complained about is Newton wasn't a really great writer. You have to read through, because sometimes he says something and it sounds like he said something else, but then you have to read through it and say, oh, okay, I get what he's saying.
Check this out yourself. So, what did Newton say about momentum? Well, first, there were a couple of definitions. So let's talk about some of these definitions first. So again,
what he didn't say was F equals ma. He didn't say that. The thing you keep putting in his mouth.
And this is from the Mathematical Principles of Natural Philosophy by Isaac Newton, also known as the Principia. And the definition of momentum, it comes in 2 parts. First, the quantity of matter is the measure of the same arising from its density and bulk conjunctly. Basically, density.
So that was a great piece of crud, right? I mean, that's the prime example of what the fuck did he just say? The quantity of matter? No, we're not even talking about that. We're talking about energy. But obviously, he's just saying it's made out of something, okay, material. And it can have a density. It can be thick with this materialness, or it can be thin with its materialness.
Density times volume, that gives you mass. So that when he says quantity of matter, he's talking about what we just call the mass of an object. And then
no, he's talking about the mass per unit of space. That's density. So it's not just about mass. It's about how packed the mass is, how close the pieces of mass are.
Definition 2, the quantity of motion, this is what Newton calls momentum. The quantity of motion is the measure of the same arising from the velocity and the quantity of matter conjunctly. So momentum is
mv.
Velocity times that quantity of matter, the mass. So mass times velocity. This is Newton's definition of what momentum is. So
quantity of motion. Probably a better way to say it, frankly, because then you understand it's a quantity. The force is a quantity. Momentum is a quantity. Things possess the quantity. They have it. And then we're back to the Descartesian statement that there's the same amount of this movement stuff in the universe. And when you put it in a big thing, the velocity is slow. When you put the movement in a little thing, the velocity is fast.
Momentum, Newton's definition of momentum is just the momentum is the mass of the object times its velocity. But there's a couple of important points about this and a couple of properties about this that are especially highlighted when we hear what Newton has to say about conservation of momentum. And this is in Corollary 3. So we've got Corollary 3 here. Again, you can check to make sure that I'm not misrepresenting this at all. I've written it on here, so let's kind of go through this. The quantity of motion, momentum, which is collected by taking the sum of the motions directed in the same parts and the difference of those that are directed in contrary parts, suffers.
Yes, will tell you how straight your car travels. So again, he's not saying there's unmotion, subtracting motion, canceling motion. He's saying if you go this way, and then you turn and you go that way, you'll end up back where you started. That left and right are opposite dimensional spaces. And so if you're trying to steer a bicycle, a stagecoach, whatever we have to use to go with his analogy, you're steering your horse. You have to pull on the reins to get him to go right. And then you have to pull on the reins to get him to go left. You have to apply a real force. There's no unforce.
No change from the action of the bodies among themselves. This is Newton's statement about conservation of momentum. And
okay, no, it's really not. But okay, play your game, okay? I wasn't arguing that Newton's statement on conservation of momentum, by the way. I'm arguing only that, yes, momentum has to be conserved. I always mention Descartes because Descartes was really clear about it. Descartes clearly stated, okay, God took his finger with a certain amount of momentum in it and he pushed the universe. And that's all that's in the universe is what he put in. There is nothing else. And if you want to watch energy, you just watch it go from one thing to another thing to another thing to another thing, and you can never make more of it and you can never destroy it. That's not Newton, but it's Newton encompassed those ideas. Newton revered Descartes.
Let's dissect this a little bit. Okay? When we're talking about momentum and the momentum of a system of multiple objects, if I have two objects, and let's say we've got objects.
So again, this is just a yin-yang argument. Nobody's arguing that there isn't these relative circumstances, that if you go this way and then you go that way, you'll end up going no way, okay, the same way. That they balance. It's not that they undo each other.
Object 1 and object 2. And let's say we've got the momentum of object 1 and the momentum of object 2. If those momentas are going in the same...
So this is just, this is just some boring textbook bullshit. Yes, of course. And again, but you're not going to do the actual experiments you're proposing and pointing out how you can make more extra free momentum. So do the example where you say, I take a 5-ton train, I plow it into something having no motion, 5 tons. And now I have a 10-ton train that has half the kinetic energy. Now you have to explain where it all went. And you're going to have to explain that somehow it bent the metal without using its momentum.
Direction, we add those momentas. If those objects, let's say this is object 1 with a certain amount of momentum, and this is object 2 with some momentum going in the opposite direction, then I subtract the...
Right, and they don't really subtract, right? So we know that if I have two objects and I force them to stay stuck to each other, so if I use a material that does deform, for example, we know that the energy will stay inside the material and it will twist and turn and bend and flex, and all of the energy will be converted into heat. So there will not be any undoing of the energy. There will not cancel. The energy will go back into the universe in some other direction. It will leak out of the objects as heat. Just as the car crash, the energy leaks out as a bunch of metal flying around and a bunch of heat coming off the crash. The crash has changed from something having these directions into something having all kinds of directions. And all you're saying is there's going to be a certain amount that are going to tend to go in this way, and there'll be a certain amount tending to go that way based on the momentum.
The magnitudes of those momentas. Okay. In Newton's model, we're saying we're taking the sum of the motions, the momenta, directed towards the same parts, moving in the same direction, and the difference of those that are directed in to contrary parts, going in opposite direction.
These are just turning right, turning left. There's nothing magical about it. I turn a little bit to the left and then I turn a lot to the right. Well, then I'm going to go in the direction of the right turn. I didn't undo anything. There is no unenergy.
Okay. So when we talk about momentum in Newton's model, in the standard physics textbook definition, direction matters. Okay. Momentum is also only conserved.
The fact that direction matters does not give you the liberty to pretend the gun undoes the bullet. Or the bullet undoes the bullet. I could use a zip gun, shoot two bullets in opposite directions. One bullet does not undo the other bullet. They are both expanding into the universe. They are both creating pressure in the universe. They haven't undone each other. There is no such thing as zero momentum in that experiment. There's a lot of momentum in that experiment.
When we only have internal forces acting on the system, that's the suffers no change from the action of bodies amongst themselves. If I have two objects that are moving in two different directions, and they slam...
Right, so I hit a stick with a baseball from one side, and then I hit the stick from the other side with a baseball. You don't say the two baseballs have no energy. I had to create the energy that went one way. I had to create the energy that went the other way. Those energies are still in the universe. The universe has to create them in the wobble of the stick. The wobble of the stick will be showing you the energy of the two baseballs. They didn't undo each other. You're just converting the energy that had a direction into energy that doesn't have a direction. And that's all you're doing.
Into each other. So let's say it's object 1 and object 2. If object 1 is running into object 2, well, by Newton's third law, every action has an equal...
Well, that's Newton's poorly articulated law, because frankly it has nothing to do with opposite reactions. If I give away, I have $10, I give it to somebody else. There's no opposite reaction that made me poor. I became poor because I gave away my $10, okay? Things give away the momentum they have. They exchange it. So two things meet, they combined for some amount of time, and depending on how much time they're combined, they will share their momentums and then leave. And there'll be some percentage of that sharing. Like I said, if I stick them together permanently, then they'll share it equally, okay? And if I allow them fly apart or bounce, then they'll bounce unevenly, but the total momentum will remain the same.
Opposite reaction. If object 1 slams into object 2, object 2 is pushing back on object 1 with the same amount of force.
All right, so there's no pushing back, okay? You have to give something energy for it to move. It can't move until you give it to it. It is not resisting motion. There is no resisting motion except in friction. None whatsoever. In space, I throw a baseball at another baseball. The baseball that I threw it at isn't providing any resistive force. It's merely saying, are you going to give me your money or you're not going to give it to me? And the fact is, in space, it'll give it the money. It'll take the $10. I'll have no dollars. It'll have the $10. It'll go off. And I'll be stuck going nowhere. There was no resistance to change. There was no resistance to the entire event. None of that happened. There was no inertia problem.
And there will be a transfer of momentum.
Simply, that is all you need to know. There's nothing else that you need to state in the third law, is that momentum is transferred. That's it. There isn't anything else to know.
Okay. We can change the direction of object 1, and we can change the direction of object 2. So each one individually goes through a change in momentum, but the system, if I add together those momentas, again, direction matters.
So this has nothing, again, this is clearly nothing I'm opposing in any way whatsoever. So this is all duh.
I have to learn how to add momentas that are going in different directions. Then the total momentum of that system will be conserved.
Right, and the argument is, and I'm sure Newton knew it too, if I have an explosion, I can't put heavy things next to the explosion and get more momentum out of the explosion. That the explosion only has a certain amount of force in it. It's going to produce a certain amount of force. A certain number of little bits are going to be flying in the universe. And the fact is, I can't change how much energy or momentum I get out of that event by putting heavy things on the spring, or putting heavy things into gravity, or doing any of that stuff. I can't change. I can't get more out. I can only get the amount I put in. The force I put in is the force I'm going to get back. The end. And you're claiming otherwise. You're claiming I can get more energy out of the explosion by putting heavy things around it than putting light things, or vice versa. Exactly the opposite in some cases.
Again, the quantity of motion suffers no change from the action of bodies among themselves. If it's just objects interacting with each other, that system will keep the same total momentum. So
right, and there's no argument I've ever made indicating otherwise, because I'm the one arguing you can't destroy momentum. You can't create it and you can't destroy it. You're stuck with it. The V and the mass don't change reality at all. There's always some place. There's big V, little m's, and there's little m's and big V's, and that's always the case. You can always trace it. Every motion has big V, little m transfers, and those transfers are explicitly just that. There is no squared term.
Momentum is conserved when there are only internal forces acting on the system. In the following discussion from the corollary, Newton gives some specific examples. So, thus, if a spherical body A with 2 parts of velocity is triple that of a spherical body B. Well, let's say that object A, let's say it's got 2 parts of velocity, so velocity equals, let's call it just 2 meters per second, just for simplicity, is triple that of a spherical body B. So the mass is 3 times the mass of B. So this is object A.
I thought he said exactly the opposite, that you're crashing a small thing into a big thing.
Mass of A, velocity of A, and the mass, let's say that's 3 kilograms. And let's say there's another mass, B, that only has a mass of 1 kilogram. So thus, if a spherical body A with 2 parts of velocity is...
So this has 2 parts of velocity. So it has twice the velocity. I mean, let's call this A, right? Oh, he made this A. He put A forward of B. Okay. All right.
Triple a spherical body B.
Triple a spherical body B. So it's 3 times the size and it's going twice as fast. I don't think that's what he's saying, but whatever. Let's see where it goes.
Which follows in the same right line, so they're going in.
So what? Who cares? So the same right line isn't going to do you any good. I mean, those are obviously additional momentum, so obviously we don't disagree on those. There's no unmomentum involved.
The same direction with 10 parts of velocity. So this thing's velocity is 10 meters per second. the motion of A will be to that of B as 6 to 10. So if we do mass times velocity, so momentum.
So he's just giving you the ratio of their velocities, which doesn't mean much.
Momentum equals mass times velocity. For the momentum of object A, that will be 3 kilograms times 2 meters per second, giving us 6 kilograms meters per second. And the momentum of object B will be 1 kilogram times 10, giving us 10 kilogram meters per second.
And who cares? I mean, if I just put B in front of A, then they never even hit each other ever. So what is this experiment about?
Of momentum. Suppose then their motions be of 6 parts and 10 parts, and the sum will be 16 parts. They're going in the same direction, so if I add these up, the total momentum of my system will be 16 kilograms meters per second.
Right. So again, he's going to try to argue that somehow this debunks something I've ever said, which is impossible.
Okay. Therefore, upon meeting, when they run into each other,
the little one's going faster than the big one, okay? Even though it has less moment, no, it has more momentum. It's going quite fast by comparison.
if A acquires 3, 4, or 5 parts of motion, B will lose as many. There's a transfer of...
No, there's no losing, okay? Both of them will have a total that's going to remain the same. So yes, they have contact, they will exchange momentum, and depending on how long they're in contact, if you put glue on them, they're both going to leave at the same rate, right? So if we use Velcro and made them stick to each other, so clearly he's talking about an elastic collision, not an inelastic collision.
Momentum. So let's say that object A gets, let's say, 5 parts of motion. So its momentum went from 6 kilograms meters per second to the momentum of A is now 11 kilograms meters per second. Well, then B will lose as many.
Right. So I've only argued 7 million times that that's all you can do is exchange momentum, like money. And it doesn't matter whether you have nickels, dimes, pennies. It just matters how much total money there is. One atom going 1,000 miles an hour is exactly the same energy in the universe as 1,000 atoms going 1 mile an hour. That's Newton.
So object B, it did have 10 kilograms meters per second of momentum, but it's lost 5, so now it's only got 5 kilograms meters per second of momentum. But the sum is still 16. The sum remaining will always be of 16 parts as before.
Right. So there's absolutely nothing here anyone could ever show where I said anything different, ever.
But then he goes on. If the body A acquires 9, 10, 11, or 12 parts of motion, therefore after meeting proceed with 15, 16, 17, or 18 parts, the body B, losing as many parts as A has got, will either proceed with 1 part, having lost 9, or stop if object A has acquired 10 parts of motion, so its total momentum of just object A is now 16, object B will stop completely.
Yeah, so we know this doesn't really happen, right? I mean, there's no real experiment where you could actually say we're going to make it stop a little bit, we're going to make it, we're going to have a half of Velcro, or we're going to have a full Velcro. It either sticks or it doesn't stick. It's either elastic or it's not. So, I mean, it's kind of a silly argument to say that somehow I could vary how much transfer there is, because we really can't vary it much.
Or, if object A gains 11 parts to its motion...
All right, so it can't gain 11 parts if A only has 10. So that can't happen.
Well, object B is going to be going backwards. So...
So there's no way that can happen. So I'm just saying you can't physically do that. So this is back, when maybe Newton thought there was some still capacity for something to give more energy than it has. But I don't know exactly why Newton would explain an experiment where something has 10 of something and it gives something else 11. I mean, realistically, not possible.
It will go back with one part having not only lost its whole motion, but, if I so may say, one part more, or will go back with two parts because the progressive motion of 12 parts is taken off. So basically, what Newton is
describing is an experiment that can't be done. Just frankly. Okay, it's either going to be elastic, that is, you're going to reflect. And the reflection will equal, real energy. And Newton's basically saying that right now. He's saying the reflected energy is real in the sense that I gave something a piece of energy I don't have. I had 10. I gave it 11, so I gave it some imaginary extra bit. Okay? And now I'm going backwards because, I have to account for that extra bit I gave away. But what the hell? I'm just saying, I'm sorry. Yeah, if this is Newton's argument, it's pretty fallacious because he doesn't have any experimental evidence that he did this.
Directly saying here is if these objects after the collision are still going in the same direction, we have to add up their momentas to get that total of 16.
And the whole thing is premised on the idea that somehow something gave away what it didn't have. Something with 10 gave $11. I'm saying if that's what Newton believed, then I'm disagreeing with Newton, okay? That nothing can give away more money than it has.
However, if object A, let's do the gaining 18 parts. Object A started with gains which one?
16 parts, but whatever. So yeah, you just I'll have to go and read this because it's hard to imagine Newton would actually suggest you can give something more energy than you have.
On here gains 12 parts of the motion. So object A started with 6 kilograms meters per second of momentum, gains 12. So now
it's 12. So it only has 10 to give, and now it gained 12.
Now object A has a momentum of 18 kilograms meters per second. Object B would have to be going backwards with a momentum of 2 kilograms meters per second.
I agree that it would have to go backwards if it gave away extra free money it didn't have. So yes, I'll agree. It would have to go backwards, but I'll again state that what example is he using? I don't think he sat there with a Newton's cradle giving both objects velocity and trying to get one object to hit the other one that's going faster. So all we really have is the Newton's cradle. So I take a Newton's cradle, I can't make something leave with more momentum. So go ahead and show me a Newton's cradle example where you make free momentum.
That would be the subtraction part. They're now going in opposite directions, so we have to subtract those momentas to properly account for what is the total momentum of this system. And so the sums of the conspiring motions, 15 plus 1 or 16 plus 0, and the differences of the contrary motions, 17 minus 1 and 18 minus 2, will always be equal to 16 parts as they were before the meeting and reflection of the bodies.
So maybe Newton's saying these two objects are hitting each other. But, it's not clear from how he's reading. He's reading it sentence by sentence, and so it's not clear what the whole paragraph is saying. So again, I'll go back and try to find that.
So I'm sorry that was really, really wordy, but I really needed to iron out this point. For momentum, in Newton's model of momentum, you're arguing that Newton believed in giving away more momentum than you have. So somehow Newton believed that an object could give another object more momentum than it had. That's what you're overtly saying. The object has 10, and it gave something else 11.
Now, I'm just saying on its face, I don't know why Newton would believe that was possible. So I don't think you're reading it right.
Direction matters. If those objects are going in opposite directions, we have to subtract those momentas. Or equivalently say, if this is my positive direction, and I've got an object moving this way, its momentum will be negative.
So again, there's no such thing as negative momentum. There's just momentum in different directions. And it's just a dimensional argument that, yes, turning left can undo turning right. But just like the sun is producing photons now in both directions, the sun isn't saying one side is negative photons and one side is positive photons. It's not part of the reality. They're both real photons. 2 photons, not 0 photons. 2. 2. 2. All directions. 2. 2. 2. 2. 2. Not 0.
Direction for momentum matters. Okay. So again, just kind of summarizing Isaac Newton's model of momentum. The definition, momentum.
Right. I'll summarize it. He believed that something with 10 momentums could give something else 11 momentums, apparently, by your reading. So on its face, silly.
Momentum is mass times velocity. Direction matters, so if the objects are going in the positive direction, we call that a positive momentum. If they're going in the negative direction, we call that a negative momentum. And this momentum is conserved.
And it's just right and left.
When there are only internal forces acting on the system.
This is a Feynman imaginary, this is like borrowing from the future. So something with 10 momentums borrows from special energy source, gives something else 11 momentums, and then later on pays it back. Or some kind of crap like that. Sorry, too silly.
What about the alternative model that has again been proposed online? Well, here are some of the key features as I've been able to understand them from, seeing these comments.
And numerous videos.
Their definition of momentum is that the momentum is equal to the mass times the magnitude of velocity. Basically,
there's no magnitude of velocity. There's just velocity. So I don't know why he threw that in there.
The mass times the speed of the object. And their claim is that momentum doesn't care about direction.
That's right. The bullet doesn't care that the gun's going the opposite way. The gun doesn't care that the bullet's going the opposite way. It has nothing to do with it. The gun is real energy. The bullet is real energy in the universe. You have to account for both events.
I've heard this many, many times in comments and things like that.
You can't make the same explosive device create different amounts of energy. You can only make it less or more efficient in moving big objects that you can see. But it creates the same heat. Every explosion creates a certain amount of heat value. And you can have less of it converted into heat and more of it moved into motion, or vice versa. But you can't change its total energy. So if you're going to do an experiment and say, look, I got it inside of a cylinder and there's 2 pistons. If the 2 pistons can both move, the explosion creates an amount of energy. The pistons move with half the energy each, okay, at a velocity. Now if I fix one of those pistons so it can't move and now the explosion happens, all of the energy has to go this way. And the other object's going to leave with twice the velocity. Because the amount the explosion produces is always the same. And if you have a device for ensuring that it all moves in one direction, in one plane, it will move on that plane.
If I had
the heat will be like a laser beam. Okay, that's all you're really saying. You're going to try to take photons that are scattered all over the place, and you're going to try to focus them into a beam where they're all going the same direction. That's what motion in large objects is that you've taken energy that could be any direction and you've made it all go the same way.
Had 2 objects going in opposite directions, and let's say this one has 200 kilograms meters per second of momentum. And this one is going the opposite direction with 200 kilograms meters per second of momentum.
Now you have created 400. That's correct. So if I had the explosion between them, they both fly off at 200. I can't fix one of them so it can't move, put them inside a barrel, and say this one's going to leave with 200. No, it's going to leave with 400.
Their claim is that the total of this would be 400 kilograms meters per second of momentum. That's the total momentum of this system.
That's right. If it's inside of a bubble, it's going to produce pressure both ways on both surfaces. One surface is going to push all of the material this way, and the other one's going to push all the material that way, and that's going to be the total pressure, is that expansion. There's 400 momentums of pressure, 400 foot-pounds.
Don't care about what direction the objects are going in. Another claim that they've made is that this momentum can be stored in things that are not moving. Even though momentum is...
Energy is stored in things that aren't moving. It's stored in batteries quite reliably. You know how much capacity the battery has. You put the energy in, you get the energy back out. The idea of storage really has nothing to do with this subject. You're claiming it stores kinetic energy. I'm claiming it stores momentum. We're not arguing about the fact that it's stored energy. I don't think we are. I mean, I think you'd have to be a crazy psychotic lunatic to say you're arguing that there aren't storage devices. Reservoirs, for example. Lots of things store the energy. We can both understand how it is stored. I'm storing the water in the reservoir. I'm storing the gravitational weight of the water. What's complicated? You say it has kinetic energy. I'm saying it just has momentum. That's the difference. You're saying if I put light things in front of the water, I'll get more energy out than if I put heavy things in front of the water. That's the difference in our theories.
Mass times velocity. The claim is if all the particles that are moving inside of that object, they store that momentum or something equivalent to momentum.
Well, what do you think is being stored, for fuck's sake? You don't understand storage? You don't understand chemical storage. You don't understand electrical storage. You don't understand water storage. What about storage do you not understand? If I push two magnets into each other, two north-facing magnets, I'm storing the potential, okay? Because we know that the two forces are going to be pushing against each other, and I'm basically storing pressure. The pressure is still there. It's pushing. Something has to constantly say, stay there, stay there, stay there, stay there. It has to constantly do work on it to keep it there. But it's work that's circular. It's work where there is no heat loss. So the work is continuous. So I take a tuning fork and I force the two magnets together. They just stay in that uncomfortable position with a lot of pressure, but the steel absorbs it and just sends it back and around and around and around and around. And it can do it for 10,000 years, and then I could just push the magnets out, they'll fly apart. I mean, come on. I have to argue about a concept of storing energy. I can't believe I have to argue that there's a concept called energy storage. Oh, God. Face palm.
And, for example, a compressed spring will store that momentum, and when the spring pushes back on those objects, it can release that momentum. Again, this is the...
And it only has a certain amount. A certain amount of spring compression is a certain amount of foot-pounds of pressure. So that's all I have. So if I put a heavy thing on the spring, I can't expect that I'm going to get a different momentum than if I put a light thing on the spring.
Claim from this proposed model online. And that this replaces the need for our textbook understanding of energy. Again, the claim from this group...
No, it replaces, it assures you that Newton was correct, that momentum is the mechanism, and that there is no need for any squared or halves or any other functions placed on them. All there is in the universe is big M's and little V's, or big V's and little M's. That's all there is. Momentum makes everything happen in the universe. Everything is a momentum exchange. Every contact between any two things in the universe is going to be an exchange of momentum. It is not going to be an exchange of kinetic energy.
Group is that kinetic energy is just made up. It doesn't actually correspond to anything physical.
Right, and the evidence is in 400 years you haven't produced a single experiment demonstrating it takes 4 times the fuel to go twice as fast.
We want to compare these two models side by side. Again, the differences, the key differences in these models as I see it, is that in Newton's model, the model that's used in every physics...
I'm going to argue whether it's Newton's model, so yeah, I have to go read what you read and see if Newton was really saying an object going 10 can give 11 momentums to something.
Physics textbook that's been written since Newton kind of came up with this formulation is that momentum direction matters. We add momentum.
Again, it's irrelevant. Yes, of course, turning right is different than turning left, but that's it. It doesn't have anything to do with the fact that both require energy. You can't turn right without applying a force. You can't turn left without applying a force. Both of them have real momentum.
In the positive direction, and we subtract momentas in the negative direction. Whereas this alternative model, momentum doesn't care about direction. Another key difference is that in the classical physics model, momentum is conserved when there are only internal forces acting on the objects. As long as all of those forces are...
Right, and so in my model, momentum is always conserved. It doesn't matter whether it's internal or external. It always is the same amount of momentum in the universe. You can never make the universe produce less momentum. You can never make the universe produce more momentum. I could turn everything into little tiny things moving, and they would move very fast. Or I can have the universe made out of big giant things moving very slow. And it's always going to be the same amount of momentum. Because the universe is a closed system, frankly.
Or internal, we're not getting any stored momentum in some other form or anything like that. During that interaction, as long as there are only internal forces, looking at the motions of those objects, even during the collision, that total momentum, as described, including direction, should stay the same. This alternative model, well...
Obviously, the energy is being stored, so when I compress something, it stops. Everything stops moving. There's a moment where everything stops moving. I throw something into gravity. There's a moment where it stops moving. It's because all of its momentum, all of its energy has been lost to its position in gravity. Okay, gravity consumed it. It took it. And now it's going to reacquire it by falling in the gravity, by free falling. So it has no momentum because it gave it all away. It lost it all to the friction created by gravity. It's fighting a force. The force consumed its momentum. I mean, come on. So I'm certainly not saying there isn't a position where everything is frozen, in a condition, compressing a spring. There's a position where all the energy is now in the spring, no doubt about it. And now we have to just wait for the spring to expand and give the energy back.
If something compresses a spring, that spring can store some of the momentum. So the momentum of the objects would...
It obviously is taking all of it. It's consuming all of it. It's consuming all of its momentum. The thing is coming to a complete halt. And the difference between regular friction and a spring, the spring isn't deformed permanently. It isn't lost as heat. The spring has the energy, and now it will give it back. A substantial amount of it back. At least in some cases, 85%, 80%?
Decrease in this particular way. So we're going to look at some specific experiments that test out these two claims. We're going to be using some of my motion sensors. There have been questions in the past of, are these motion sensors accurate? I just posted a video testing out these motion sensors and showing that, yes, we can show...
Whatever. So he wants to argue the detail of his motion sensor. Now, the whole point is that its velocity is changing. They're rolling carts, so obviously there is some friction. They're further away or closer to the objects that's testing them. So that's part of the scenario. And what you really need is the velocity just before impact. You need its real velocity, not an average velocity, not a velocity taken over, 10 milliseconds or some stretch of time. So again, there's lots of things that could be argued about whether or not you're getting the right velocity numbers. But whatever, just pretend you have perfected the concept. Okay. When you're debunked, okay, frankly, what's your explanation going to be? I mean, if I make your bridge fall down, what's going to be the excuse?
That they're reliable as long as we're using the data that is low noise. We can say that both objects are being tracked in the cases that we're going to be looking at. So again, they're reliable sensors, and we're going to look at specific cases that test out the differences in these models. Does direction matter?
So these are free momentum experiments, right? So I've said the real free momentum experiment to do is find an object that's just quite heavy enough where it still moves a little bit. Because by their theory, I crash into that almost barely moving object and I double my momentum.
The properties of momentum. Can momentum be stored in something that's not moving, or is momentum just conserved as long as we are only looking at the internal forces? So let's set up the experiments and see which model comes out on top. So let's have a bit of a look at our experimental setup. We've got two carts, and they're each going to be tracked by one of the motion sensors. So we've got a motion sensor here, and we've got a motion sensor over here, and we're going to call this one cart 1, and this one's going to be cart 2. We're going to be able to change the masses of these carts. We're going to be able to change how they collide with each other. Right now I've got repelling magnets on both of them, and we're going to be doing this under a number of different circumstances to identify cases where these two models, the classical physics model of momentum and this alternative model of momentum, ideally look for cases where they make different predictions and see which one of them makes accurate predictions, which one matches with experiment. I did a previous video, I'll put a link to that here, testing out these motion sensors. Even though they're aimed at each other and even though we can sometimes get some interference, we can detect when we are getting interference with these sensors based on some really, really noisy...
So the only good thing about this video compared to the previous one is at least this image is big enough to do frame rates on. So we'll see.
Velocity data. So if we see that noisy velocity data, well, we'll take another run. We won't include that highly suspect data. We'll only use clean data for these experiments. So let's get started with this. We're going to need to have the masses of these objects. So for the first trial, I thought cart 1, I'm going to add some masses to it. So let me grab this. Make sure we zero this. And cart 1 has a mass of 558 grams.
So make it put on, okay, let's see, do 4 times as much. 4 times the mass. Because that way you'll get 170. You'll get 1.7 free momentum times 1.7.
Cart 2 has a mass of 308 grams.
308. What did he say? I don't know. I forgot already.
So we're going to need to have the masses of these objects. So for the first trial, I thought cart 1, I'm going to add some masses to it. So let me grab this. Make sure we zero this. And cart 1 has a mass of 558 grams. Cart 2 has a mass of 308 grams.
Why do they have different weights when you haven't put anything on them yet? Well, whatever.
Okay, so let's record those masses. Make sure that we don't miss anything. So mass 1 was 558 grams. Mass 2 was 308 grams.
So it's lighter. He's going to hit a lighter cart.
And we're going to also put that into our into Logger Pro, so we can actually...
Right, so we're going to do this all synthetically in a computer, which I'm not terribly interested in. I just want to know the velocity and the masses. I don't want to know any of that other crap.
Measure on the fly what are the momentas of these objects. So I've got 0.558 for mass 1 and 0.308 for mass 2. And just to kind of note the kinds of measurements I'm making, for momentum 1 is just the mass of object 1 times the velocity of object 1 as measured by that sensor. Momentum 2 is the mass of object 2 times the velocity of object 2, and this sensor, I've reversed the direction of this sensor, so both sensors are saying to the camera's right is the positive direction. We've got the total momentum, just saying momentum 1 plus momentum 2, and again, if they're going in if they're going to the camera's left, those are going to read as negative momenta. So this model is using the Newton's classical physics model of testing this momentum. And lastly, in case we want to actually measure this, we're also going to talk about kinetic energy. Now, I should mention that Newton's model didn't include anything about kinetic energy. That wasn't a formulation that was really well developed at the time. Newton did think that momentum was...
It was opposed by Newton, okay? Let's just keep mushing about. Newton opposed it. The Newtonians completely defeated Leibniz. Leibniz was buried, discredited. Nobody showed up to say goodbye. Newton was buried as a god.
The most fundamental quantity of motion, and we really find that we need both momentum and energy to fully describe.
Right, no, you don't need, right. So the Newtonians clearly stated what I'm stating. Your formula is a free energy formula. Everything breaks. It breaks levers. It breaks everything. Everything breaks, okay? Everything's all of a sudden a free energy machine. It doesn't work. And then Leibniz's retort was, your theory's free energy, because he was claiming, that his answers were correct when they clearly weren't. 4 times the fall in gravity is not collecting 4 times the force.
What's going to happen to these systems. But again, for this video, we're just going to focus on how these two models of momenta compare with each other. Okay, so let's set these up for a first run. Also note that I have included these markers at 10 centimeter intervals, and I'm also going to put some timestamps onto these videos. So if you don't believe the sensor measurements, you can use those times and these distances to actually measure what the velocities of these carts are by hand. You are welcome to do that if you think that these sensors aren't working. But let's do an initial data run. So I'm going to start the sensor.
So initial data run, what? Not in the middle of the arrows. Okay, thanks. Very helpful.
Okay. So again, we've got some pretty good data. It gets a little noisy at the end when we lose tracking, but during, just before, during, and after the collision, that momenta's, those velocity data seem quite stable, so I'm pretty happy with these results. So let's look at what...
This doesn't look quite stable, but whatever. You say so. The red is now faster and the blue is slower. And he's got them going in the same direction. Well, we'll see what he says.
We get for the momentas in each of these cases. So note that the momentas on the bottom, we've got velocities on the top, momentas on the bottom, and those momentas should just be the mass times the velocity. So for example, for object 1, its mass was 0.558 kilograms. And to get the velocity, to get the momentum, we multiply that by 0.308, and I got 0.172. This seems to be matching up. So momentum 1 was, before the collision, was 0.127 for object 1. Object 2 had nothing, so the total momentum, both the textbook model and the alternative model would agree that the total momentum that we're starting with is 0.172 kilograms meters per second. So let's put that into these windows here. So 0.172, 0.172. They both agree for this before case. Okay. Well, let's look after. So just a little bit after that collision. Well, we've got velocity 1, velocity 2. If you want to kind of go through and verify that the computer is calculating the momentas on the bottom properly, you are welcome to do that. But we've got the momentum of object 1 is 0.051, momentum of object 2 is 0.120, and the total momentum is 0.171. And both the textbook model and the alternative model would agree with these, because both of the carts were only moving in the positive direction.
All right, so fine. I'll come back and do the second half of this video. So he's doing the... We don't have any vector problem in the sense of vector versus scalar. So when they say vector, I should have realized that all they mean by vector versus scalar is you can subtract momentums, okay? And that somehow a subtracted momentum isn't real energy. It's not extra energy. So whatever you're using to subtract from something else, it's not real new energy. So you can, in fact, create something going 3 this way and something going 10 that way, and you can only use 7. Because that's all there really is just 7 that way. So somehow 7 that way can create 3 this way and 7 that way. I mean 10. 10 this way and 3 that way can create 13, and somehow I don't have to account for the 13. Because it's only a net 7. So a net 7 in can create 13 out. That's their theory. And I'd say quite obviously, yeah, no, not buying it. Find a bigger sucker. Because, yeah, you're not fooling me. Anyway, till the next time and such and so forth and whatnot.